Okay, everybody, here is our next video on photoelectric effect. Okay, so here's this thing called the photoelectric effect. Essentially, what this is. Let's say I have some substance. Doesn't really matter what it is right now. Um, just a plate of anything that's a pure substance or a not pure substance, whatever it is. We've got a plate of stuff. Let's say I then shine a light on that plate of stuff. Okay, so we've got a light, and I will see. Oh, I don't have purple. Dang. I was going to do purple, but blue will have to do, I guess. If I take this flashlight and just shine it on this plate. Okay, so there's kind of our macroscopic view of this. If we were to zoom in really, really far, right? Zoom in really far, our um, we've got our nucleus, right? We'll take a look at one atom nucleus, first energy level, second energy level, whatever, third, fourth, fifth, and then up to the edge of the atom with our infinite energy level, n equals 1, 2, 3, 4, and that's n equals infinity is right out there. So that's escaping the atom essentially. Right? If I were to zoom in on this, let's take our electron. Oh, let's put it in n equals 2. Why not? Let's put our electron in n equals 2. Okay. If I have this photon, and we'll kind of model photons as this little packet of energy. That's how we model photons, really. It's kind of this wavy form in the middle of a line. So this is our packet of energy. This right here, that's our photon. But that's how we represent light, as being both the photon that it is, the particle, and being a wave that we know the light can behave like. Okay, so this photon comes in and it hits our electron. What does the electron then do? Well, the electron, it gains the energy, so it jumps up to maybe a higher energy level or something like that. And then what eventually happens is that electron will jump back down and then emits a photon of its own. So we get this photon emitted of its own when it jumps back down. Okay, we know this. We've done this, all that kind of stuff. I'm going to go backward now. What if to go backward though and say, what if when the electron jumps up, what if it jumps all the way up? Right? What if our electron gets beyond this infinite energy level? Right? And we've kind of already explored this. We've explored an electron, how much energy does it take to get out of the atom? So then the electron, and I won't use blue for this because blue is the color that we had for our light. Our electron now has some kinetic energy that it escapes with, right? And we have done this. We've looked at this conservation of energy equation, right? The energy, let's get a thinner pen. We've looked at this energy initial, right? Energy final. Initially, we've got the photon moving, so HF. Then we have, essentially it's whatever, I'll call it the freeing energy, whatever energy it takes for this electron to get free, plus whatever kinetic energy is left over. Okay. Let's take a look closer at this freeing energy now, though, because before I told you what n equals 2. Maybe I'd said that was negative 3.4 EVs. But maybe n equals 1, maybe this is hydrogen, so negative 13.6 EVs. As a reminder, you have to know that number, the 13.6, as n equals 1 for hydrogen. That's the only one of those energy level numbers you have to know, though. Okay, so this freeing energy, that depends on what level it's on. So we can say that, the energy in is equal to whatever energy it takes to get out of the atom plus the energy that it has once it gets out of the atom, right? That's the kinetic energy. Well, this freeing energy, that depends on what atom it is. And it depends on what energy level it starts on. Because, it won't take as much energy for it to go from level 4 out of the atom as it will from level 1 to get out of the atom, right? That's more energy that it takes. 4 is less energy, 2 is kind of in between, all that kind of stuff. So we call this freeing energy, whatever energy it takes to get free. We will call this the work function. This is called the work function of a substance, of a material. And a different substance or a different element will have a different work function. Um, so we can take a look at this, right? This work function, and essentially what this turns into is we take a look at this, the work function. This is the energy it takes for an electron on the outer levels to get free. So that means that this is the maximum kinetic energy it might have, right? Because maybe you get an electron that's lower down, is on a lower energy level, so it takes more energy to get out as opposed to, so because it has to take the energy to get up to that fourth level, and then it's on an even playing field with the electron that starts on the fourth energy level. So this work function is essentially, it's the minimum amount of energy required to shoot an electron free. Minimum energy to free an electron. So those are the electrons kind of on the upper levels. It might take more energy than that, but it's not going to take less energy. That's the minimum energy it takes to get an electron out of the atom. So if that's the minimum, then that means that this kinetic energy, this is the maximum kinetic energy it might have if it starts on one of those higher energy levels. Because if it starts lower, then more energy goes to escaping than goes to its movement once it has escaped. Okay. So what AP has done is they give you an equation, and I'll pop over to the equation sheet now. Right, so that's the front. If you go down to the modern physics side of things, one of these equations looks very similar to what we just were looking at. K max is equal to HF minus, and then here's this Greek letter phi, PHI. So we've got kinetic energy max is equal to HF minus phi, and that phi is that's this freeing energy. That's whatever energy it takes to get out. That is the work function, but we also call that phi. So they actually they solve for kinetic energy max. So they say K max is equal to HF minus phi. And I'll highlight phi the same color. All right, so you can relate this. Phi is whatever energy it takes to get free. It's the energy, it's called the work function. It's over here. Another term for it, and I'm sorry, there's so many terms for this, but AP will use them all interchangeably. It's called the binding energy sometimes. We'll see work function more often, but you have to know all of these names. It's the freeing energy, it's the work function, it's the binding energy, or it's called phi, is the Greek letter that stands for it. So that depends on what the substance is, all that kind of good stuff. Okay, so this is this thing called the photoelectric effect on the microscopic scale. Let's take a look. I'll slide back over left at the macroscopic scale. Right, because each one of these rays of light coming out of the light, right, that hits an atom. So that hits an atom there. That hits a different atom. That hits a different atom. That hits and every single ray coming from this light hits a different atom. So we get an electron from that atom that gets freed with some amount of kinetic energy. We get an electron from this one that gets freed with some amount of kinetic energy. All right, that happens for all of them. And the higher up it starts, the more kinetic energy that electron will have. So maybe one of them starts on a really high energy level and makes it all the way over there. It's just faster. Or maybe one of them is on n equals 1 and it doesn't make it very far because it took more of the energy to escape the atom than it did to actually move after it has escaped. So that's the photoelectric effect. Okay, let's take a practice problem with this. Photoelectric effect practice problem. All right, let's say that I have, okay, let's say we've got a plate over here, and on that plate, um, let's say that we have a block of, let's call it sodium. Sodium is, it's kind of this dark gray metal. Yes, I know sodium would explode if it really was in the air, so this is not real. Um, okay, so we'll call this sodium, which is element symbol for sodium is Na, stands for the Latin version of natrium, but we in English call it sodium. Okay, so let's say that we have a light is incident on a plate of sodium. And let's say that the wavelength of this light is 100 nanometers. Okay, so 100 nanometers would be the incident light. Basically, if we're taking a look at this, what type of light is this? Where on the electromagnetic spectrum does this fall? Well, remember, visible light is 400 to 700 nanometers approximately. So if this is just shorter than visible light, right? It's just shorter than that, means it has a little bit more energy. So this will be ultraviolet. So this will be in the ultraviolet spectrum. Okay. So now that we have this UV spectrum light incident on a block of sodium, what's going to happen? All right, we'll get some electrons that get released. Okay, maybe this one has a little bit more kinetic energy, is coming from a higher level. Maybe this one is coming from the second level, so it has a little bit less kinetic energy. But right, we're looking for K max. How far can it possibly go? Okay, so if we're looking at the photoelectric effect, and I zoomed so we have our equation there, right? We know that the kinetic energy that they might possibly have maximum is HF, and right, this is the incident light minus our work function, minus phi. All right, kinetic energy max. Sorry, I should say, what is the maximum kinetic energy an electron might have? Okay, an electron might have. So there's our question. So okay, we're looking for this. That's what we're looking for. Okay, so if we're trying to solve this, right, K max equals and then HF, but we don't have frequency, we have wavelength. So remember, we can turn that into HC over lambda by relating, right, velocity is equal to frequency times wavelength, but velocity for the speed of light is c. Okay, so we can relate that there. Minus our work function. What are we going to do about work function? Well, this is something that AP would have to give you. But I wanted to not give it to you straight away so you could see my process with this. Essentially, I told you it's sodium, right? Since we know it's sodium, here's what I'm going to do. I'm going to Google work function of sodium. And we want it in, right, this is a number in joules. Yay, great, it's a number, but that's kind of annoying. So I'm going to click the in electron volts, 2.75 electron volts. Okay, back over to our problem. We now know that for sodium, work function is equal to 2.75 electron volts. All right, so we can plug that right in there, 2.75 EVs. All right, so let's keep going. Kinetic energy maximum is equal to, all right, we have HC over lambda. Well, remember our equation sheet tells us H times C. If we look back up to the front page, we have H times C right here. And since our work function's in electron volts, which of these options do you think we'll use? The one in electron volts. So we'll use this one, right? 1.24 times 10 to the third. Essentially, that's 1,240. So I'll just say 1240, and that's electron volts times nanometers. If you take a look back over here, electron volts times nanometers. Okay, and then over wavelength, Well, we were given wavelength was 100 nanometers. Okay, minus 2.75 electron volts. Okay, nanometers on top and bottom, those cancel. So if we have kinetic energy max, all right, we have 1240 divided by 100. So that's going to give me 1.24 EVs, electron volts, minus 2.75 electron volts. Oh, I'm sorry, it's not 1.24, it's 12.4. My apologies, 12.4 electron volts minus 2.75 electron volts. Okay, so we get that our maximum kinetic energy that it could have is whatever 12.4 minus 2.75 is. Let me get my calculator. 2.75, 9.65 electron volts. Okay. And that is very much a problem or a type of problem that AP would have you do. I've seen this on at least 5 or 6 free response questions is something like this. What's the maximum kinetic energy given the wavelength, given the work function? All you have to do is plug it into HC over lambda and plug in phi for whatever you're given for whatever that material is. In this case, it was sodium. Sodium's work function, 2.75. All right. I just want to go over one more thing that you might run into with this photoelectric effect before the end of this video. Photoelectric effect, another thing you might run into. Okay, so let's say we have our plate. All right, we've got our plate with a light that is incident. All right, I like to draw it like this with a flashlight. And we've got our incident light on our plate there. Okay, but what if, right, because as these electrons leave, we have, because these are electrons, they're negative electrons, they're negative. So what if I put this in essentially in between parallel plates, charged parallel plates? And what if I make this one negative? If I make this one negative and I make this one positive, what's going to happen to those electrons? All right, electric field goes out of the positive into the negatives. There's electric field, but this is an electron. All right, negative electrons, what force will they feel? They're repelled by their negatives and they're attracted to the positives. So these electrons will experience a force, and I'll say it's an electric force, back to the left. So we see these electrons, they'll move out, and if I have done my job kind of right, the light is incident, and then we get shot off, but then it gets repelled by this plate over here. So instead of just shooting off to nothing, this electron, it shoots off, and then it experiences that backward force, so it'll just eventually stop and then get attracted back over here to the positive plate. I mean, maybe it hits the material on its way back. Who knows? But we like to look at this in terms of this thing called stopping, right? It stops and then it reverses direction. So we look at this in terms of this thing called stopping potential. So that's a term you have to know. Stopping potential. And this stopping potential, right? Stopping means the electron stops. Potential is, right, if negative, we call this at 0 volts. This one is at, I don't know, let's say 3 volts. Potential refers to electric potential difference. Potential difference, which in variable speak we say delta V, delta voltage. So the stopping potential is whatever potential it takes to make the electron stop. What is really nice about voltage, and specifically about this unit of electron volts. Okay, so I'll get the force that way. But about this unit of electron volts. Right, let's come over and I'm going to look back at the previous problem, just remind myself of the numbers. So we got that the maximum kinetic energy when this UV light was incident on sodium, we said that the maximum kinetic energy was 9.65 electron volts. Okay, so let's assume this is the same problem. All right, we've got 100 nanometer wavelength, and we've got kinetic energy that is 9.65 electron volts, and that's our kinetic energy of our electrons. The maximum kinetic energy, I should say. Well, here's what's really nice about electrons is I'm going to replace this 3. That was a number I just came up with off the top of my head. If we want the electrons to stop, an electron with 9.65 electron volts of kinetic energy will be stopped by 9.65 volts of electric potential difference. So if I make this 9.65 volts is our electric potential difference, our stopping potential is whatever this is. Essentially, this number tells us this is why electron volts is really nice. 9.65 volts to stop an electron. That's essentially what this unit is created for, is this photoelectric effect. It's one of the nicest, neatest applications that we could ever have. So if that previous question, all right, this question over here, if instead of asking what is the maximum kinetic energy an electron might have, if instead of asking that, maybe it asked us a different question. Maybe it asked, let's see, I haven't used brown or orange really on this page. Maybe it says as the question, what is the stopping potential? The stopping potential for 100 nanometer light on sodium. Maybe that's the question instead. Well, guess what? It is exactly the same problem. You do exactly the same work. You just, instead of ending here at this kinetic energy max, you don't end there. You say that kinetic energy maximum is 9.65 electron volts, which means the stopping potential would be stopping potential would be 9.65 volts. And that's your answer, right? Because it takes 9.65 volts to stop one electron. And I shouldn't say one electron, to stop an electron. That's the unit of electron volts. That's how many volts an electron can go through before it'll stop. Okay. So that is it for this video. I will go ahead and pause the video here. This will be continued on a second video for photoelectric effect, looking at some more special applications, things like that, some practice problems. If you have any questions, let me know, but otherwise, we'll see you next time.